for the introduction. So I'm Felipe Gorostiaga, and today I will tell you about this runtime verification engine factory that we have called MOLA. One goal of our group in a few years ago was to implement a language for runtime verification that would be easy to extend for new application domains. So after some work and due to some reasons that I will tell you in a minute, we came up with this, which is an implementation done as an EDSL in Haskell. And it was pretty good. I mean, it is easily extensible, obviously, but it also has a few drawbacks that you can probably already see. So in this work, we wanted to tackle that, and to do it, we introduced a figure of, we unfolded the work in two. So on one hand, a theory engineer would write the data type for the application domain in Haskell that would get compiled, and then a specification engineer will write the specification as it was intended in the first place. So in this talk, I will tell you how and why we did that. So a little bit of background first. In runtime verification, we take a specification, and in static time, we derive a monitor from it that we then run alongside the program that we are evaluating. And the monitor will receive observations regarding the program, and it will produce results. And if you do all of this, if you define your specification in terms of streams, what we are doing is stream runtime verification, which is what we are working on. LOLA is a language for doing runtime verification based on streams, in which the system data is captured on input streams and output streams are defined over other streams data. And the main aspect of LOLA, the main characteristic, is that it poses a clear separation of the temporal and the data aspects of the language. So the defining expression of an output stream in LOLA is either the application of a function to other expressions, or a ground value, or the value of a stream at the current time, or the value of a stream with shifted by an offset. And if you do that, you have to specify default value to use when the offset falls off the trace. So even though LOLA separates the temporal and the data aspects of a language, when we went to implement it, we realized that we were investing a lot of effort on parsing constants, variables, functions, doing type checking and stuff, and not so much on the temporal part of the language, which is that we were interested on. So it ended up looking something like this. And to overcome this, that's the reason why we decided to do it as an EDSL in Haskell. An embedded DSL is essentially a library in the host language. And since LOLA is an incomplete language because it doesn't impose an application domain, what we have done is using the types and functions from Haskell to complete the language. And once we have done that, we deep embedded the resulting complete language back into Haskell. And this implementation, we have called it HLOLA. And it benefits from the type checker, the parser, the ecosystem of Haskell together. But of course, it came with some drawbacks too, right? As I showed you before, this is an HLOLA specification, which obviously doesn't look like a specification, right? And it has many drawbacks. For example, to begin with, we have duplicated values because we had to treat them both at the language level and as symbols. We also have a preamble for every specification that was always there, and we couldn't get rid of it. Obviously, as I said, this is a Haskell program, and the syntax of the part of the specification diverges completely from the original language. For every minor change in the specification, we had to recompile the whole stuff. And also, finally, and maybe most important, is that the errors were very cryptic. I mean, the errors were in the realm of Haskell and not in the realm of LOLA, which is what we expected. So we wanted to get rid of these drawbacks, but we also wanted to maintain the extensibility of the EDSL. So we came with this intermediate solution that which is this meta interpreter, or the engine factory that we have called MOLA. MOLA is built obviously on top of HLOLA, and in HLOLA we have defined a data type for the LOLA expressions, which is pretty simple. An expression can be either an element of the theory or the application of an expression to another expression or a stream access. And we can think of a LOLA expression as a tree in that data type. So the first thing we did was get rid of the Haskell values and define a stringly typed expressions in which anything can be applied to anything, and the parsed tree only has symbols as the leaves. But now we have to come up with a way to give meaning to these symbols, and that's when the theory engineer steps in. And the job of the theory engineer is to define a table binding every symbol of the theory to a Haskell value. And for example, given this theory of Booleans, we can already define and make sense out of a LOLA specification like this one. But then we realized that we can also use the HLOLA constructors as part of the theory itself. So we have bound these constructors of the LOLA language to symbols, and that let us get rid of LOLA specific operators, and the stringly typed tree that we parsed now is agnostic of HLOLA. And the only difference is that now an HLOLA expression doesn't have a corresponding tree with the same shape, but instead, in this case, the HLOLA expression leaf 5 is the application of the symbol leaf to the symbol 5. In LOLA, it is useful to have integers, and in fact, they are necessary because you have to use them for the offset expressions. So you need integers, and so we had to come up with a way to deal with them. And one thing we couldn't do was to add every symbol to the theory and bind them to the integer. So what we did was obviously writing a return function that would take a symbol. It will look it in the table of the theory, and it is found. Then it returns that value. Otherwise, it tries to use the Haskell's read data class to get a value of the corresponding type, and if it succeeds, then well, that's the expected value. And doing this, we could also get rid of the Boolean ground values because they implement the read data class. So our Boolean theory now it's even more minimal than before. And now with the theory and the stringly typed parsed data type, all we have to do is replace the leaves in the expression, and we get a similar expression with the same shape, but where the leaves are already Haskell values. So from this, given a theory table, we were able to decode the expression with the leaves with Haskell values. And now that we have this, which is a tree of applications, all we have to do is evaluate it. It will return a Haskell value, which upon inspection, we will see that it is an HLOLA expression. If it is not, then there was a type error of some kind somewhere, and it will show up. So now we can go line by line on this example specification and see what our tool would do at every line. So for the first line, this is just a definition of an input stream with a name and a type, and that is what we do, which we just create an HLOLA stream. The same goes for the second line. And when we come to the third line, we see that it has a defining expression, which we easily parse to this stringly typed expression. We use the theory table to convert it to a similar tree with real Haskell values. We evaluate it, and we bind the result to the name of the stream. And that's it. That's essentially how it works. But in the definition of x implies y, we can see that the symbols for x and y appear. So when we are translating this, we want these two to resolve to the recently defined streams. So at this point, these streams have to be part of the theory, right? But since a stream can refer to itself, we have to do that as we are processing the specification. But we can do it recursively, and everything works. So as we are processing the specification, we add every symbol of the defined streams to the theory themselves. And when we wanted to include the HLOLA constructors as part of the theory, we found out that we had to implement polymorphism and type inference. So now our theory tables not only have ground values, but they also have an annotated type, which can have type variables. And we had to implement type inference and unification to make sure that everything was well typed. So given a stringly typed expression, the first thing we do is use the information of the types in the theory to infer the types of every leaf. And once everything is well typed, and we have checked that, and everything could unify, and there were no problems, now we're ready to decode the tree and evaluate it and bind it to the output stream. And that's essentially how it works. So in summary, what we did in this job is introducing this middle player, which is the theory engineer that will write all the Haskell code with the data type for the application domain. And we have separated that role from the specification engineer, who is in charge of writing the specifications. So, in conclusion, we have seen that in our work we saw that empirically that an EDSL is a fast implementation of a prototype language. It lets you play with the constructors and polish it, extend it, and very easily. And it's useful when the developer of the EDSL is also the one who uses it, because they are proficient probably in the language itself. But an end user will usually expect an interpreted implementation. So the error messages have to be in the realm of the tool itself and not the underlying language. And usually losing the whole power of the underlying language is acceptable. So with Lola, we found a way to move from an EDSL to a finally interpreted language, maintaining extensibility with symbol tables and with polymorphism and type inference. And we were able to do all of this without losing type safety. And if you want to play with the tool, it has a dedicated branch on the mother repository of HLOLA. And yeah, you can go there and play with it. And yeah, and that's it. Thank you.
Thank you very much. So, any questions?
Thanks for the talk. And well, if I understood it well, I think that you specialize the meta interpreter for a given data theory in order to get something which is, I guess, more efficient and faster and so on. So how do you do that? I mean, are you using a particular partial evaluation or a specialization technique? Are you using any tool for that? Or are you doing it that by hand? How do you do this specialization?
Hi, can you hear me now? Yes, there's two steps, right? You have to define the theory by hand in Haskell. And once that is done, what you get, you compile it with GHC. And what you get is an interpreter for a given application domain. Well, I mean, we have done heavy use of the reflection package of Haskell to make sure everything is well typed and there's no ugly runtime errors. But that's how it works. I mean, given the application domain, the specification engineer can use those types and functions in their specification. MOLA is in that sense meta because it doesn't come with. I mean, it does come with a few application domains, obviously, but you can. A Haskell programmer can easily extend the application domains. That's what we are selling. I mean, it's not fixed, and it's very easy to add new theories. So it comes with Booleans, integers, doubles, and I mean, if you go to the repository, you will find example theories for handle UAV flying monitors and applications to the blockchain. So, but those are examples, and then if you have a new application domain, you should, if you are a Haskell programmer, you should easily add your new data types and functions for them to be used in the specification by a non-Haskell expert.
Okay, if I understand what you say is that it's actually not a partial evaluation or a specialization. You just add more information. This data theory. So anyway, I think that perhaps partial evaluation or specialization could be useful to get something more efficient. It's been used for domain-specific languages in the literature precisely for that. So you write an interpreter, and if you want to get something a more efficient interpreter, you can specialize it for a particular strategy, for a particular theory, for a particular program, for a particular anything. It's a way
into optimization,
something which is faster, which runs faster without any special effort.
I see. What you are proposing is if you are using only integers or only bitmaps, then you can make it more efficient if you are aware that those are your application domains, right? Yeah, sure. I mean, we should definitely take a look into that. Yeah.
Just maybe not a question, but just following up. I think so. In monitoring applications, if I'm not mistaken, if I remember properly, even the non-super efficient implementations would process like thousands, even tens of thousands, hundreds of thousands of events per second. So the difficulty that I think was accomplished with this work is to refactor a tool that is built for, say, for example, UAVs into a network processing monitoring tool. And with tools like this, you can do that in like 2 days, for example. And then your users will be, for example, network processing or say denial of service attacks software developers or engineers. And 2 days before, the tool was specialized for UAV flying. So it was on board of actual UAVs. So it's not so much about speeding up the tool, which could be great, but this is not the purpose. Is how do you transform a tool that was conceived for embedded systems into network processing, for example, or blockchain analysis. And with this, it can be done in like, 200 lines and maybe 2 days without having to go through a complete refactoring of the whole software. So I think it's about flexibility, not so much efficiency, right?
More questions? Can I ask you a small question? So, Haskell to generate the code. Then you're also going to have to do the Haskell libraries as well, right? At the end of the day. Imagine if you wanted to plug this in UAV. Would that be too much in terms of space?
But I mean, you're worried because of the fact that you are using Haskell, right? As they are. Yes, probably. I mean, obviously it depends on the Haskell binary, right? But I'm confident. For example, when we did the EDSL, it was pretty bound to Haskell, right? I mean, Haskell is a good language for EDSLs, and that's why we chose it. But now I'm pretty sure that we can rewrite the tool in a different language, for example, C++, something that targets efficiency and speed. And now, of course, the final user will never notice that. And also the specification, the theory engineer, the one who has to be an expert in the underlying language, I think a different language will not be so harsh with them. I mean, in other words, we did it in Haskell because we came from an EDSL, but you can, I think, from now on, it might be a good exercise to move to a different language like C++ and keep all these, all this architecture.
That will be more because you are consumers.
Sorry?
It will be more because your consumers are going to be people who have experience more in C++ than in.
Probably, yeah.
Thank you very much.
Thank you.